Hey, welcome to the Linux channel. So I shot various episodes on network protocol data structure like IPv4 header and then TCP header, UDP header and so on. So anytime if you write user space networking applications or else some kind of system software related stuff, or else if you are doing any kernel side packet processing stack or your own custom stack, these data structures are really useful because you can directly map your the packet bytes or else the bytes of your PDU corresponding to this data structure. You don't need to rewrite again, and you just need to do is you just need to use this data structure. So as a part of this series, today I thought let me take a very simple data structure, which is the data structure which holds that Ethernet header. As you understand, Ethernet header contains typically like three headers as such, so which is like our three fields. You have that destination MAC, source MAC, and then you have the type field, and then you will have that payload. So if you hop onto this kernel source, you can find here it is inside include UAPI Linux if_ether.h. You should also understand sometimes if you read any books, especially which are quite old, almost a decade old, those books may refer towards kernel source of 2.2 or a little older than that. So in that case, it may be in a different hierarchy. It may be include Linux if_ether.h or so. It may not be in UAPI. So this you have to make a note always when you refer any books. You should cross check with the real kernel source so that where it exactly corresponds. In that same assumption, if you watch this video maybe after a decade, you may not find it in this location as well, because always the kernel source is evolving. They are doing always changes and refinements and architectural changes and stuff like that. So it always happens. So you have to keep this in mind. Never take anything too serious. You have to see how far it is applicable to the current version of Linux kernel source. So that's what it is. So if you see in this file, you can see it has this struct eth header, and that you have this h dest and h source, so which corresponds to destination MAC and source MAC. Since MAC ID is a hardware firmware assigned address, they are mentioning as a hardware destination, and the H maybe stands for hardware or else it may stand for hardware. Let's just take that as an assumption, because they have not mentioned as MAC address, but we can understand that this is nothing but MAC ID. So if you see here, h dest is having this length, eth a length, and if you go on top, it has this defined here. So eth a length is 6 bytes, because MAC ID is 6 bytes, and then eth hardware header length is 14. I think in this case the H stands for header, so you can see here H length is 14. So this is the total length of Ethernet header, which is 6 bytes and 6 bytes and then 2 bytes. So 12 plus 2 bytes, which is the type field, totally it is 14 bytes. So that's what it is. So if you go here, so that's what it is. And then you have this protocol part. So you should always understand anytime they may mention here and there, as if you go up, they may mention the length of the payload, and you can see here the frame and stuff like that. You should always understand, if you are new to networking, don't call generally the packets which you see here in Wireshark. Let me open Wireshark. So anytime if you see generally packets in Wireshark, people call them as packets. So in sometimes it is okay to call as packets if you are dealing something with IPv4 context, or let me just capture few packets, and let me refresh this page so that we get these packets. Yeah, so you can see here you have these packets. So you should always keep in mind, especially this is quite easy to understand if you have done any CCNA or so. In that way, network admins can never get this wrong. But I have seen often always software developers, especially network protocol developers, always they make it wrong. They don't understand what to call as a packet and what to be called as a frame, because right away if you come out of the college, you are never you will never have an idea to use that right jargon. So this is very important. Never call just like that these frames what you see here as packets. As you can see in Wireshark, it calls them as frame. The frame means essentially you have that layer 2 header. In this case it is Ethernet header, and then within layer 2 header, the payload of layer 2 header is your the network layer, and within the network layer the payload is your transport header and then its payload, and then the payload of your transport header is let's take example like TCP. So you can see the transport header is TCP, or else let's take example like this DNS. The transport header is UDP and its payload is your DNS request or reply application layer protocol. So this is what it is. So don't get confused with session and other layers in between. So directly you can understand session and presentation layers and stuff like that. Just directly understand after the transport layer you have the application layer. Usually the application layer is some protocol in user space. So anytime you do socket programming and stuff like that, what essentially you are doing is you are dealing with the application layer protocol, and then you are sending it via TCP or UDP, and then it will get encapsulated by the Linux kernel. You are not going to do as a part of socket code. The Linux kernel is what essentially it does that. So that's what it is. And then it gets packed in multiple layers, and it's just like you send any package in Amazon or something. So anytime a vendor sends the package, they may put it in some bubble wrap, and then they may also pack it in Amazon box, and then the product may have its own cardboard box, and then he is going to put that product inside an Amazon package. So it is again getting wrapped up. So this is what essentially is happening. So if you have an application layer protocol, it is wrapped up by its surrounding transport layer, and then it is getting wrapped up in its corresponding network layer, and if it goes in some VPN or something, again it is going to be wrapped up in multiple network layers, because it's essentially it does tunneling in a case like VPN. So finally after it does all these things, so you have this the real hardware layer, which is the data link layer, because the data link layer and the physical layer are tightly interlinked. So what you can see and touch is physical layer, but whereas what you directly use it as a part of physical layer addressing is data link layer. So this is what it is. So you should always consider it's an integral part. The software layer of physical layer is data link layer, whereas the hardware part of data link layer is your physical layer. That's what it is. So essentially this is what is happening. So anytime you capture in Wireshark, consider always the direct whatever the bytes you see as a part of each individual entity is frame. So if you see here, you have this Ethernet header, and this is what it its corresponding data structure which is used. So in Linux kernel, if you are curious, maybe you can search in various cases like how it is getting used. So if you see various network stack, you can see here at multiple places it is getting used. You can see here in this case SKB of ethhdr, they are using this API, so that it if SKB has this Ethernet header mapped, okay, if it has been mapped, so that is why you see here they are doing this reset SKB MAC header. If it is mapped, it will able to parse with this API eth header, and it is returning this eth header over here. So as you've seen, I've just randomly picked an example, so you can find it in various instances in the Linux kernel source as you go through and traverse it deeply. That's what it is. So if you are curious and interested about the API eth header, you can see, let us see where it has been implemented. You can see here include Linux if ether.h, and in this case you can see here it has this APIs. So these are very tiny APIs, and you see their eth header, and it takes the argument as skbuf, the function parameter. and then it uses this internally another API skb MAC header, and then it gets that the Ethernet header of that corresponding skbuf data structure. So this is what it is. So if you click again further, you can find its own definition, skbuf skb MAC header. You can see here. So you can find various such APIs. You can also pull its network header, you can pull its transport header and stuff like that. So this is one among that set of APIs. You can see here skb MAC header, and it is doing skb of head plus it is doing this offset and it is pulling that MAC header. So sometimes you can do it in manual way. There are multiple ways to do that. You can also traverse through skb data. Usually I do in that way, or you can do in this way, because if it is not known whether it's header has been set, if that head is exactly aligning towards that frame, beginning of that frame, in that case it is safer to do a check and then do directly through skb data instead of doing this way. So I do in that way, whereas you can do in this way. The reason also that at multiple places skb exists in a different way. So suppose if you go to the website, let me show any links. So you can find, so for quick references I have added various architectural pictures. Let us go to any of this. Yeah, you can see here. So what I have done is, these are just image SRCs of that original source which I got it in Google Images, so that I have not hosted in my website and get into any copyright issues. So in case if you are curious, you can go to that respective websites. I have mentioned all the links and then image links as well. So if you see, this is you can find it in Google. So this is the overall architecture of packet traversal in the Linux kernel stack. You can find various variants and examples like that. So at each case, what happens is, when skb is in this module, when the skb is in this module, when the skb is in this module, it all depends. So in each case, skb data is going to be pointing at a different location. Suppose if you go to IP output or IP input, skb data may point from the beginning of IP header, which is the network layer, and if you go to device.c, which is outside of IPv4 stack, skb data may point to the Ethernet header onwards. So this is what it is. So this you have to check, and then you have to confirm if Ethernet header has been set, because especially if you do an TX traversal, the packet it is getting formed in IPv4 stack, and it is going outside of IPv4 stack, it may not have any Ethernet header. Whereas if you do the RX path, the packet itself is coming out from NIC card inside the IPv4 stack, so its Ethernet header will be already set. So it all depends whether the packet is in IP underscore input, or whether the packet is in IP underscore output, or whether the packet is in dev.c. So most cases in device.c or netcore dev.c, which you can see here, it must have got that Ethernet header already set, or the data link layer already set, because I should not stress Ethernet header, because sometimes if you use any 4G networks or something like that, it may use point-to-point or PPP header. So this is the reason. So I should not stress about Ethernet header, because it can be any hardware physical layer dependent data link layer header. So sometimes it is to be mentioned in that way. So this is what it is. So with that, I would like to wrap up. So if you are curious, you can go through all the APIs which corresponds to Ethernet header, and this is what is the data structure. In case if you are doing any user space code, you can also use this struct, because you can also include in user space as well. So this is what it is, just like you do with IP header, UDP header, and TCP header and stuff like that. So in case if you have any questions, do reach me via email. I'm going to attach my contact details in the YouTube description. So thank you once again for watching this video. Have a nice day. Bye bye.